Thank you, Dr. Vettel. That was really some cutting-edge work you're pioneering, and we're excited to hear about it in future years. I also am excited to announce our final session that we're going to continue looking to the future of AI. So here to talk about what's next for the future of healthcare is Dr. Richard Satava, Professor Emeritus of Surgery at the University of Washington Medical Center. And he's going to be in conversation with Aaron Boyd, who is our Senior Editor of Technology and Events at Nextgov.
Covered. In position. Man down, man down. Medevac. Medevac. Scanning. Forceps.
Great. Yeah, so we'll come back to that in a bit, but very cool stuff we just watched. So let's break it down. I'm Aaron Boyd, Senior Editor with Nextgov, and join with me here to wrap up our session is Dr. Richard Satava. Dr. Satava, can you real quick, you've been working on things like this kind of emergency health IT thing for soldiers in the field. How long have you been working in this area?
I've been working in this area for 1992. What you saw was the concept video for robotic surgery for DARPA in 1992. By 2005, because everything was available at the time that you saw in there, we now have robotic surgery, we now have digital imaging, and every component of that was demonstrated in their prototypes.
Could you break down a bit what we saw?
What we saw was the surgeon in a remote location in a MASH hospital with the medic in the far forward area and taking advantage of the existing robotic, very, very simple AI technologies and so forth to be able to remotely operate on that casualty just enough to save their lives for them to be evacuated automatically back to the MASH hospital. Now we have a live patient that the surgeon is able to continue the care on and be able to save their lives. The point that I wanted to make was A, technology was available in non-healthcare fields, and B, we were able to leverage off of that, what was available at the time, and move forward and create commercial products as you know them today.
So what kind of products would the folks here in the audience be familiar with that came out of this research?
Well, you'd be, of course, the most obvious one is the robotic surgery that we have today. The commercial company is Intuitive, and there are now 5 others that are in the FDA application phase in order to get their robots approved. I'd like to make a point here, and that is that the robots are not machines. Robots are information systems. You are not your body, you are your brain. I could take your body away, and then you would have exactly the same person to begin with. So the point here is we need to relook healthcare, not from the standpoint as much in the past from the physical attributes, but rather from the intangibles. Intangibles such as artificial intelligence that we see here, the information systems that drive our robotic sensors, the new AI that's coming out, which is based upon sensors, Artificial intelligence, in my mind, is not a program. It's ubiquitous at this point in time to a point that it's invisible to most everybody. Just like on your computer, the operating system, I don't know of any of you personally who actually dive into the operating system and understand how my computer works. We just get in there and start typing. But that's the way AI is, but most of us don't even think about it that way. The sensors that are out there are actually examples of AI. MEMS technologies, harvesting information and making it available, as you saw in the previous lecture. So in the future, we're going to go more and more to intangibles. One of the things I'd like to emphasize is that most of the technologies for the immediate future were discovered in 1959 by one lecturer, by Nobel laureate Richard Feynman. There's plenty of room at the bottom. From this, we got quantum mechanics, nanotechnology, and 10 years later, we had the structure of DNA and genetics, but it was also predicted in Richard Feynman's lecture. The future of medicine is going to become invisible, as is emphasized repeatedly in the previous lectures, particularly by Mr. Safi. The next generation is going to go from what we have today, mechanical systems, to information plus directed energy. This is the direction. Why do I say that? All of the parts are in place right now. We have molecular biology, we have genetics, we have vaccinations, we have intelligent systems, and when you put them all together, we now have technology that allows us to see, feel, and manipulate at the molecular and atomic level. No one ever got sick because their kidney was bad or the liver was bad. They got sick because there was disruption of the molecules within some, but not all of the cells within these organs. The technology that's out in non-healthcare field is now in the laboratories in healthcare, allowing us to look down at the molecular level. We can use tools, but these tools are not the ones we've used in the past. Cells are 10 to 20 microns in size. That's really tiny. I don't have any scalpel that can cut with 10 to 20 microns. But I have, for example, femtosecond lasers that I can focus on, make an incision in a cell, open it up, and using optical tweezers, be able to go ahead and manipulate things inside of them, or nanotechnology probes that will allow us in an individual cell to be able to do that. You saw before from Jeannie in the Army Research Lab that she explained the closed loop feedback. We now have instruments, directed energy instruments, high intensity focused ultrasound, photobiomodulation, acoustic enoporation. These are energy systems, energy devices that allow us to work at the molecular level. For example, at the University of Tennessee, we have a clinical research program in which they give molecular markers to a cancer, astrocytoma, or glioblastoma multiforme, brain cancers. And then they are decorated with markers that have receptivity to light, photobiomodulation, and they carry various toxic agents. The molecular markers only go to the cancer cells. When they're attached, light is shined through the skull, 528 nanometers, activates them and kills only the cancer cells without causing any damage to the rest of the body. And the patient is cured. Clinical trials are already in practice. The same thing is happening with high-intensity focused ultrasound, but this is used for solid tumors. It could be in the breast, in the prostate, in the uterus, and with the same concept, but using ultrasound, we're actually able to destroy the tumors or the particular disease that the molecular markers go in. So the bottom line here is that we're using technology that's available in other areas, and my specialty is surgery, in order to be able to use energy non-invasively to cure diseases that previously required open surgery or robotic surgery. We couldn't do it without the technologies that exist today.
So where has technology come from 1959 to today that gets us closer to be able to doing these things? You said that the underlying tech has been there, but what jumps did we have to make to get to where we are now and where we're going?
Most of these are available, and this is the difficult problem we have: technology transfer and commercialization. They're out there. For those who review the literature in certain areas, AI, robotics, minimally invasive surgery, and so forth, you will see that it's there, and you will find the research problems that have been solved, but there is nobody within the commercial and industry sector to pick these up and move them forward. They are afraid of risk. They are afraid that they won't get an ROI in the next 3 months. And trying to get something that is going to be revolutionary. I do not want to make anything we have better. I want to change it, as was demonstrated before. And we have the opportunity now by taking what I think is the revolutionary concept in non-healthcare and bring it into the healthcare sector. Look around at those lectures that you saw today. Many of them showed you technologies that you'd kind of laugh at because, well, that can't happen in medicine. They already have them, self-driving cars and so forth. So we need to pick up on what's out there, find that same technology application in our laboratories that are beginning to emerge in various devices, and then find a way to transition this into a commercial sector. The government doesn't make commercial things. It does research, it does prototypes, and then it hands it off.
So that's like your time when you spent with DARPA, right? That's the kind of framework, right? Where you're
Well, that's the framework of virtually every research group, if you will. It's just that there are more high-risk ones in DARPA than there are, for example, in NIH, and they're more toward the applied science side, in addition to bugs and drugs, which allow them to take something and get it up towards the FDA with clinical trials, which is more conducive for a company to come and take that technology now that it's got FDA approval from clinical trials and move it over into a significant commercial product.
This is one of those areas where you mentioned risk before. The government generally has it's said to be risk averse, but I feel like this is one area where the government can take on that risk and would be willing to because the motivations are different.
Absolutely, there's no question. If you look at the way funding occurs for new technologies, there are two components to that. One is the private sector and the other is the government. So if this is the amount of money that is going to be needed in order to accomplish a new high-risk project, the government funds this way, and as they get more and more mature, the amount of funding decreases. In the meantime, we have the companies waiting for these new technologies, and they'll maybe give some seed funding and so forth. But then finally, when it gets FDA approval, what ends up happening is they go forward with it. They finally understand it. What have we got? The Valley of Death. You've probably been familiar with that. So the problem—
Or the Valley of Bad Health?
Yes. It impacts all sectors, not just the healthcare, but yes,
Fair.
One of our problems is transitioning a new high-risk technology that we don't have 20 years amount of data on to find out whether it really is safe or not. Perhaps this is going to be a significant area for AI in the future, simulating using computational analytics and so forth, and make a reasonable prediction based on massive amounts of data.
So you kind of going meta there, using AI to predict whether a certain AI application is worth investing in?
Well, it's not so much investing in the AI application. As I said, my view is AI is invisible. It's there, it's underneath everything. It's been there for 20 to 30 years, but nobody's been paying attention to it. We've got Internet of Things. You never thought of that, have you, as AI, but it is. And so these technologies with the AI is underneath there, and what we would need to do is pick out those good technologies to move forward with and see how we can enhance them with AI, because it truly is an enabler. Many of the roadblocks that we have is that we don't have the data that we need. This is the era of evidence-based medicine, right? We're moving forward, and we want the scientific evidence that will support that this is going to be safe for our patients. And I love the quote that Dr. Safdie put at the end about William Mayo. It's not about the physician. It's not about the technology. It's all about the patient. And if we focus on the patient and then bring the relevant technologies forward, including AI, then we'll have the opportunity, in my mind, to be able to move this needle a little bit in a high-risk area to a lower-risk area.
You mentioned that AI is often behind the scenes. You don't see it. I think we had a perfect example there in your video. There was no anthropomorphized hologram, guiding them through the surgery or anything like that. Where was the AI in that, in robotic surgery?
It was in the translation of the remote surgeon's hand motions into being able to accurately allow him to position precisely where they need to be.
Could a system, so you've been working on this started working on this back in the early 90s. I read an RFP the other day from the Army that is exactly for these kind of systems, but their issue that they're working through today is connectivity. If you're in the middle of Kandahar, can you get a wireless signal strong enough to be able to do those remote surgeries? Is AI something that could help bridge that gap? If you lose connectivity, it can take over?
There are a number of issues, but for example, if you're within 50 kilometers, then the issue becomes security, not latency.
Security of the physician or of the connection?
No, of the connection. Okay. I'm sorry, of the communication connection. It needs to be encrypted. It has to be interoperable. It has to be able to be redundant. You're going to need 2 or 3 lines in case something goes down. We've been through those issues. The problem that we have is the bandwidth that we need and the security that we need isn't in healthcare. It's in our intelligence community and so on and so forth. The soldier doesn't really need health care until that point in time that they're wounded. And so from that standpoint, health care normally sits there next to water, food, and other logistical supplies. The physician is a logistical supply. He doesn't fight. They stand back and tries to repair a wounded soldier so they either get back to the battlefield or they can be evacuated out. So with that in mind, it's hard to allocate the amount of communication spectrum that would be needed to do something like this. It takes a very large amount of spectrum in order to move this data back quickly enough so there's no latency.
Yeah. Again, could an AI system help bridge those latency gaps, or are we not there yet?
Well, I'm not that worried about the latency gap, because we can get the combat surgeon far forward enough to still be safe and to be able to project. The problem would be, is there enough bandwidth available? Is it all being used up for war fighting and so forth? And the second one would be, how secure is it that it won't get interrupted? Those are the issues I see.
And when if you're a surgeon using these remote tools, are your hands inside some gloves and you're doing this? Are you typing code into a machine? How does it actually work?
How many of you are familiar with the robotic surgery systems available today? Have you seen them? You sit at a console that looks like a video game, and you hold what are like the handles of your surgical instruments, and then you move your hand, and the robotic arm cuts precisely where you want it to cut. So you are in charge of the individual robotic arms. It is not doing this by themselves. Where AI is going to be coming forward, I believe, is one, to provide what we call virtual constraints. There are certain areas that are dangerous to put your instrument. You may injure another organ or a blood vessel or something. So these virtual constraints will alert you, well, you're going to cut the blood vessel and the patient's going to die, type of alert. And that would be something that the AI would do with very sophisticated image recognition, as well as the algorithms that would process that and determine alert or not alert type of thing.
Are we at a point or close to a point, per the quote from Dr. Mayo, where we can get the physician out of the loop? Are we at a point where AI can just do the surgery?
At this point in time, no, and I can't go into all the reasons why not. Theoretically, we should be able to have that completed for simple, non-complex procedures within the next, 10 to 15 years. There are some procedures that are so straightforward and simple.
If there's a slug in my shoulder, it can dig it out.
Right. And so, but there are other things, like the majority of surgery ends up being something that's rather complex.
So without getting too deep into that, because I want to save time for your quiz here, what is it that humans can do in the surgery theater that robots and AI can't? Is it just the instincts of knowing where to go, or why can't we just train it to perform the procedure?
Well, the problem with humans is that they're soft. They're never in the same place at the same time, and that's why latency is a problem. If I cut and it takes too long for the signal to get there, this beating heart or respiration of the organs moving relative, and I'll cut and what I wanted to cut's not there anymore. No two people are alike, and so that makes it a real significant problem as well, although AI eventually is going to be able to compensate for that.
So you think about 10, 15 years by your estimates?
Yeah, about 10, 15 years for simple procedures.
Yeah. Excellent. So let's get to this this quiz you have here set up. This is the interactive part of the presentation.
Okay, well, the technologies, some of which I mentioned here, are going to cause significant problems that no one is paying attention to right now. And we now have human cloning. What are we going to do with human cloning? Should we continue with it? Who will be able to be cloned? If we clone people, will there be enough people? We already have enough people on the planet. How can we clone more and more people and be able to support them all? We have already begun on there with genetic engineering. The first child that was genetically engineered was back in 2006. We now have what we call savior siblings. If you have a known genetic disease, phenylketonuria, von Willebrand's disease, and so forth, you can be asked, the family, will you please have another child? We will engineer them without that genetic defect. And if we can do that, then we'll be able to take some cells, transfuse it back into the disabled child, and cure them. What's the problem here? What happens if the family doesn't want another child? Who would decide that? Only the family, realizing that the disabled child will cost the government about $100,000 a year to make them able to be functional, and when with a very small single time you'd be able to cure them. Longevity. We already know how to extend the lifespan to about 1.5 to 2 times the normal lifespan in animals. It's been repeated over and over again. We can do apoptosis, we can do anti-telomerase and so forth. So there are ways that we have done and demonstrated repeatedly. The question is, should we start doing that? As I mentioned, if we do, you'd live between 150 and 200 years. What would you do for your lifespan, if you would, yeah? Would you retire at 65? Can you imagine the government paying 100 years worth of Social Security and so forth? And once again, the same problem with taking care of people if they don't die. Even if they have a healthy lifespan, we will continue to have babies and will double or quadruple the rate at which we're already expanding.
Sounds like a Kurt Vonnegut story.
Yeah. we didn't go into tissue engineering and regeneration, but we can now create any organ or tissue in your body except for your brain. If we do that, what happens? If I replace all the tissues with either parts, mechanical parts, or new grown tissue, are you still human? What makes you human? What happens if we do the reverse? We take out your brain, if it's brain damage, and we put in your memories in a mechanical brain, a computer, if you will. Are you still yourself? Am I still me? These sound stupid. But on the other hand, they're doable. Not right now, but they will be in the future. The reason that this is successful, and this is one of the technologies that really needs to move forward, is we can grow any organ. We have many, many people on waiting lists for livers, kidneys, and so on and so forth. We are printing those organs with the patient's own stem cells. We've done this in animals, and then replaced them in the animal. They are not rejected because they're their own stem cells. So all the people that are on waiting lists right now, 15 to 20% of which die before they can even get to being eligible for transplantation. Oh, I lied. We can grow brains. And this is the frightening thing. The University of Vienna has demonstrated that it can be done.
Can you grow my brain?
Not yet,
Okay.
but they have grown mouse brain. And so we are demonstrating that this can happen. This is at the early research phase. We're probably 20 to 30 years away from doing it on humans, probably more. Not that it technically can't be done, but what are the consequences of that? What are we going to do with this brain? Will we keep it in a vat and use it for computing like they did in the Matrix? Will you go ahead and put it in a robot so it will be a smart robot? Will you give it to somebody else?
Yeah, would I be able to transfer my consciousness from my brain to a manufactured one?
That is going to be a little bit harder. We have already been able to do that, as you know, with the Brain Machines Interface program. And we have people with little implants in their brain that have had prostheses, and they're able to use the prostheses and control them simply with their thoughts. Those are out there. I personally know 3 or 4 of these people.
Yeah, someone can control drone swarms, which is just...
The question is, do we go the other way from one person to another person? I don't know. And probably the biggest ethical question, at least in my mind, came up with the Blue Ribbon panel, the President's Congressional Panel on Biomedical Ethics. And it said, for the first time in history, there walks on this planet a species so powerful it can control its own evolution till its own time and choosing. So the question is, and this involves all of you, particularly on the policy level, on the industry level, and so forth. What will we choose to make the next species following humans? That decision now, we're on that tipping point where that decision is in our hands. Our next generation will start manipulating with the technologies I've mentioned and many more that are out there. And the question is, what will we make the next human? Homo sapiens is not a patient species. It's not going to wait 100,000 or 1,000,000 years to evolve to something different. So, for those of you who haven't read this book, it's very interesting. Homo Deus, by the same one that did Homo sapiens. And it's called Homo Deus because the postulate here that Yuri Harari indicated was that you and I today are gods relative to our species in the Roman and the Greek era. Apollo would go across the sky in his golden chariot. You got on your airplane to come here. Zeus knew everything and knew everybody, and you get on the internet. So we have technically evolved to a point to give us capabilities which in the past were attributed to godlike things. Where are we going to go beyond this? I don't know. I think that decision is going to be more up to you, associated with the government, than it is going to be with the scientists in the laboratory.
Well, I wanted to ask you that because
Yeah.
I didn't want to interrupt because this is just such a fascinating thing, and I hope that sinks in with everyone what was just talked about because it. But I want to, unfortunately, derail it slightly and ask you, you've been in the different sectors, public sector, private sector, research, all of these things. From your perspective, who should be making these decisions? Is this something we have to decide from a government? Is this something that should be done by researchers? Is this something the private sector will drive? Is this something that just our cultural norms will drive?
It's going to be driven by money, unfortunately. And the largest holder of money is government. And so a lot of what we as scientists can do, as I mentioned with technology transfer, is going to be, if we can get these projects funded and get individual companies interested in it, then we can accelerate this. Otherwise, it's going to very slowly mature. When the decisions come on the political level, the key in my mind is having stakeholders, the patient, the physician, the research community per se. So it should not be, in my mind, one of the, well, government's going to mandate this because they think things aren't going too fast. It's got to be a partnership. And recently in science, we have been doing an enormous amount of what we call consensus conferences. When we develop a new technology, we hold a consensus conference to determine exactly what needs to be done with doctors, engineers, computer scientists, behavioral psychologists, the whole network of people that have a stake in there. And I think the more often that we get government and practitioners and patients involved in deciding the future of healthcare, the greater the accelerated rate we can for these new technologies.
Excellent. We are over time, but I did want to just give a chance for some questions. So we can do one or two if we just go through them real quick, and then anybody with leftover questions can ambush Dr. Satava afterwards. Do you have anybody who wanted to ask one now? No? Guess they want to talk to you afterwards. All right, then. We'll wrap up with Connie.
Yeah, it's the deers in the headlight response.
Yes.